Welcome to the Semblex Solutions at Work mini video series. I am Brant Ruskowitz, the Product Development Manager at Semblex, which is a specialty fastener company in the Chicago area. In this video series, we will evaluate the latest fastening technologies available through Semblex and look at some of the potential applications for each technology. The topics for this year will focus on thread forming fasteners for high-strength steels, innovations in self-drilling fastener designs, and low capital investment self-extruding fasteners, which are fasteners for thin sheet metal where you want to increase your length of thread engagement without needing an expensive drive system. Today, we will determine the proper assembly torque for M8 Rolok HS fasteners installed into DP1180 steel with laser cut holes. Rolok HS is a thread forming fastener that was designed for use in high strength steels. If you're unfamiliar with Rolok HS, please watch our first Semblex Solutions at Work video. It's linked in the description below. Today, we are working with 1.6 millimeter thick laser cut DP1180 steel. When a laser is used to create holes in a steel part, the edges where that laser cut through become hardened. We took hardness measurements of a cross section of one of these holes, and we looked at how the hardness evolved, starting from the edge of the hole, moving radially away. We can see that close to the hole, at 0.02 millimeters from the edge, we have a higher hardness of around 47 Rockwell C. As we move further from the hole, that hardness decreases back to the base hardness of the material. In this case, that's around 40 Rockwell C. Even low carbon soft steels can still see a significant hardening from a laser cutting process, and this makes it very difficult for traditional thread forming fasteners to form threads into these materials. In order to use this fastener, we first must determine what torque to tighten it to on our assembly line. To do this, we're going to conduct drive to failure testing, which is playing in the video right now. In this testing, we're going to install the screw at a set RPM, and we're going to continue rotating until failure occurs. In this case, we're spinning at 150 RPM, and we're going to record the data from each test. We will repeat this process at least 25 times to generate enough data to have a statistically significant analysis. Now that we've gathered all that data, let's take a look at some of those torque curves and figure out what assembly torque we can use on our production line. First, let's look at the result for a single drive. There are 4 different points labeled on this graph that correspond to the figure at the right. At point 1, our torque is 0. At point 2, we've reached a maximum thread forming torque. We call this the drive torque. At point 3, the head of our fastener makes contact with our clamp materials and the bolt begins to stretch. At this point, we begin generating clamp load. At point 4, the joint fails. We must pick a torque that is higher than the drive torque but lower than the failure torque. If we pick a torque that is too low, with a simple torque controlled driver, it may shut off before our fastener seats, before we reach point 3. However, too high of a torque and we risk breaking the joint. We don't want to conduct this analysis on a single curve. We want a more statistically significant data set. What we're showing now is 30 repetitions all plotted on the same axes. From this data, we will first calculate our average drive torque and our average failure torque, which is shown as the blue lines. Next, we're going to calculate the standard deviation for both drive torque and failure torque. We'll then take our average drive torque and add 3 drive torque standard deviations to it. This gives us our lower fastening torque limit, which is the lower dashed red line. We'll then subtract 3 failure torque standard deviations from our average failure torque, and this will set our upper fastener torque limit. Our assembly window is simply the distance between the 2 dashed red lines. That's the range of torques that we could potentially use on our assembly line. Now that we have established our assembly window, what torque do we pick? We know that our customer's hole size tolerance is 7.4 to 7.6 millimeters, and the holes we tested were at the upper limit at 7.6 millimeters. We know that the drive torque and the failure torque are both going to increase as the hole size gets smaller and we near the other end of the tolerance. Because of this, we're going to choose a value closer to the upper assembly limit, because we want to make sure that our tightening torque is going to be higher than our drive torque, even if the hole size shrinks. At this moment in time, we don't know what the drive torque will be on the other side of the hole tolerance at 7.4 millimeters. In this case, we chose 11 Newton meters, and that's 75% of the assembly window. If there were clamp load requirements, the next test would be to install this fastener and then check the clamp load to make sure that the torque we have chosen is going to work for our application. For steel joints, one of our targets is often to get as much clamp load as we can. And an easy way to do this is by picking a value higher in the assembly window, such as what we have done here. However, we also need to be careful that we pick a torque that is within the limitations of our installation equipment or our driver. In this case, our driver was accurate to plus or minus 1.5 Newton meters. This means we have to pick a value to tighten that is 12.5 Newton meters or lower. Here we picked 11, so we're safe. To further reduce the risk of stripping our joint due to driver inertia, especially in a thin metal application like this one, we're going to use a two-stage drive. This means that we're going to initially install at a higher speed, and then at a transition torque, we will slow down to a lower speed to tighten. We want to pick that transition torque between the two stages such that it's higher than the drive torque, because if we slow down at that drive torque spike, our installation time is going to be really long. We want to slow down right as the bearing surface seats. Our final tightening strategy for this joint is 150 RPM until 4 Newton meters, and then 30 RPM until 11 Newton meters. What is now playing is a type of testing called serviceability testing or reinsertion testing. Many of our customers request this type of testing whenever a component that is fastened has to be able to be serviced, meaning the fasteners are removed, the part is replaced, and then the fasteners are reinserted. Reinsertion testing shows us if we're degrading either our fastener threads or the threads formed in the mating material over time as we continually retighten this fastener. We're using the same torque strategy that we developed earlier and just continually reinstalling the fastener at those parameters. We reached the 10th insertion and we're still able to hit our tightening torque. We back the screw out and then we try to insert it by hand. It's actually still too tight for us to install without a driver. Thank you for joining us for this Semblex Solutions at Work video. If you have any questions, feel free to contact us through our website at www.semblex.com or send us an email to sales@semblex.com.